Okay, but let's continue on the lesson 4. So now, as the second kind of a broader topic for today is to go through a few different geometric operations that might be useful. So there are, one of them is the overlay analysis. That might be in different, well, when you're doing data processing yourself, so you might have situations where you, for example, want to intersect two different layers to each other and basically find out, for example, those areas that are shared in geometric space in both of these layers. So there are different ways. So we have intersection, we have union. So in union, basically what we are doing is that we are basically merging two spatial layers together like this, and then you might even do symmetrical difference. So kind of keep only those features from the layers that do not overlap each other. And then you might take a difference where you actually use geometries from one layer to cut a piece from another one. So these kind of typical tasks or queries might be need to do at some point. So we will take a look at how can we actually do those kind of things. Then the second topic is how to aggregate data. So the idea is to use a dissolve. So basically to combine different, well, in our example, we will basically kind of merge all travel times. For example, basically take all the travel times where their travel time is 15 minutes from the city center, and then you kind of take all those geometries, put them together and start doing something. So this is kind of a dissolve functionality that can be, or function in GeoPandas that can be used to do these kind of things. And the last thing, if we have time, we will see how we can simplify geometries. So basically have as an input, this is Amazon River from South America, we have as an input layer, and we can see that it's quite detailed in a way that it has a lot of these river curves and bendings in here, and we basically just as an example see how we can highly simplify this geometry by using this simplify function, which might be at some cases useful. This is especially useful thing if you have something like the whole Finland and the boundaries of the whole Finland, and the data file is really large, and you are doing, for example, a whole map of Finland where you don't actually need that detailed information about where the coastline is, for example, going. So if you have that kind of thing and you just want to make a kind of broader map using a bit more simplified geometries, which is much more faster to render and create the map, for example, so you might actually simplify that. Yes, but these three topics are what we are covering next, and let's start with server connection error. So we start with the overlay analysis, and the idea in here is that we have two layers of data. So in the data folder here we have Helsinki borders, and then we have the travel times to railway station, basically covering the whole region. Okay. Yeah. So let's import GeoPandas. Let's import. Well, we don't need to import that. But let's import from Shapely a function called speedups. This is because, well, as you from the really first lesson of this AutoGIS course, so we saw that actually what is running under the hood, all the geometries, so there are these shapely geometries. And now as we are doing fairly computing heavy things when doing the overlay analysis, we can actually speed up to make queries a bit faster. So speed up queries. This should be on by default, but this is anyway something that we can enable. So shapely.speedups.enable, which is something useful. But let's read the data. So determine the file path. So let's define that the border file path equals to the data. Let's go here. So data, and we have this Helsinki borders shapefile. Helsinki borders.shape. And the other one that we want to use is this travel times. So it's grid file path equals to data travel times to 5975 375. So this is just an ID for the destination, and we have railway station.shape. You can copy paste the file from here as well, the name, but I use it now like this. And then let's read the files. So these typical tricks. So first let's read the grid. So gbd.read file grid fp, and let's read the Helsinki borders. So hel is gbd.read file border fp. And let's finally plot those layers together. So we can say that let's plot the grid as the basic layer. So grid.plot, and the face color should be gray. So let's give it a gray color. And then on top of that, let's plot the Helsinki borders. So hel.plot, and we should plot it on top of this grid. So we specified that the axis x equals to x that we get from this first one. So then we are actually plotting on the same figure, and let's say that the face color equals to none. So let's not use any face color but the edge color. So what is the color of the line of the polygon? So the should be blue. And when we run this, let's see if everything works correctly. I don't see anything. Well, now we have the functionality. So now, as you saw, we don't have any figures coming out. But if I will now take this and create a new cell. But if I do magic command matplotlib inline and now do the plot, so now I should have something coming out. Yes. So this is the reason for having this magic percentage mark matplotlib inline. So this is basically what we have. Yes.
That's only for notebooks. You don't need it for Spider or anything else.
Yeah, no for Spider. So Spider always plots out things. So this is mainly related to notebooks, and well, using the notebooks or the Jupyter Lab. For some reason, we had with Dave, we thought that the plots should come out in the Jupyter Lab automatically, but as we can see, it doesn't. So this is, but anyway, so what we want to do is that indeed we have this grid in here, and then we have this shape in here that basically covers the borders of Helsinki. So what we want to do is that we want to take an intersection between these two layers. So what does that mean is that we are doing this kind of operation where we have the two layers, and from those areas where they overlap, we basically merge those layers together. So let's see what happens when we do this. The really first thing that always when you do analysis or any data processing having multiple layers, so you really want to check and ensure that the coordinate reference system matches. So let's check if the coordinate reference system between these two layers matches. And for doing these kind of tests, so you already practiced using this assert function. So using this assert is a good way to check. And what we want to check, so we want to make a test that the Hel, which is the Helsinki borders, Hel.crs equals to grid.crs. And how this assert functionality function works is that if they match, it doesn't produce any errors, and the kind of script that you have or the codes continues basically not normally. But if they don't match, we can basically specify that what kind of error message should be given. So we can, for example, in this case, say that CRS differs between layers. So let's see. Okay, in our case, it didn't produce any error message, so we are basically good to go. And just to demonstrate, so let's print Hel.crs and the grid.crs. So indeed, because they are identical in here, having this projection, so there are no problems and we can continue as this assert function demonstrated. Good, but now let's see how we can actually do the intersection. So intersect layers. So we can create a variable called intersection, and that and how we can do is that we can use this overlay function from GeoPandas. So gbd.overlay is the function that we want to use. And basically how that works is that you provide two layers. So kind of the left GeoDataFrame, which is the grid, and then the right layer, which is in our case the Helsinki borders in this Hel variable. And with this parameter how, we can specify that, okay, what kind of overlay analysis do you want to do? So do you want to make intersection, union, symmetrical difference, or difference, for example? And in our case, we want to use the intersection. So we specify that how equals to intersection. And now when we run this, it takes some time, but basically what we should have as an output is a layer where these two layers have been intersected. And we can take a look at that by plotting. So we can say that intersection.plot. We can specify that the color should be blue. So now the overlay analysis was run, and now we can plot it, and let's see. So now as an output we can see that we basically took these parts from the data, and indeed we have that those two layers kind of merged together, with the intersection. And as you can see from the boundaries, what it does, this intersection actually, is that it really basically uses the boundaries of this one. And it cuts basically all the geometries from this grid. So it's a different than doing kind of selection based on geometry. It actually kind of shapes the geometries based on the other layer. And this is how we can see, so that they are not these kind of grid cells that we have, but we actually have merged those two layers together. Let's see how the data actually looks like. So let's take the intersection dot head. So now we can see that, okay, we have the grid values, so these are again these travel times and distances. But what we have now as well in here is that we have the geometry, the information from the other layer. So, well, actually, so the, let's see, here we have the, so L.head to, so we can see that from this layer we have this GML ID, name Finn, name Swedish, national code or something like that, and then the geometry. So actually those variables were basically came as the last parts in our new GeoDataFrame after the intersection. So this is basically what happens. So you kind of get the geometries together, but also the attributes from the layers in here. Now let's, as a final step, so let's save the output file path as a GeoJason file. So let's create an output FP, which will be the path to the file. So let's say that the name is travel times to, well, railway station and only Helsinki.GeoJason. So now we save it as a GeoJason file, which is commonly used data format, for example, when fetching data from different APIs or web feature services, for example, so you can get a JSON actually out of from there. So let's save it using GeoJason driver. So now we use the intersection dot to file, and now we specify that to which, so save it to this file name and use the driver GeoJason. So this is how we can basically save it as a GeoJason file. And when we do this, it takes a few moments. But now what we should have, if I update this, is that we have this new travel times to railway station Helsinki GeoJason, which is, well, basically the same thing as the first one that we used previously. So it was actually an output from this command in here. So this is how we can kind of do intersections using this overlay analysis. There is a link in here to GeoPanda's documentation, so there we have a lot of different kind of examples how these different things work, and you might want to, well, if you're interested, so you can take a look at the documentation actually from here and see what kind of things you can do with the overlay analysis. Do you have any questions about this? Yes.
So is there any rule of thumb as to when we should save as a GeoJason versus a shapely or shape file?
Basically, they're shape files were the kind of, well, they still are quite a lot used data format for storing spatial data. But nowadays, especially because what is problem with shape files is that it is a kind of package of multiple files. But whereas this GeoJason is actually quite nice, there are certain limitations also regarding the shape file. So for example, this attribute table, which is stored in this dbf file, it cannot be larger than 2 gigabytes. And well, nowadays when we have a lot of data, so actually 2 gigabytes of data might go quite fast. But this GeoJason file, so this is basically, it's just a text file with certain structure where we have certain input, a certain kind of, well, structures and the columns, and basically the features are written there in a certain format and so on. So this GeoJason is, I would maybe even prefer that one. Because it does not have any limits. It's also nice in a way that you only have that one file that you need to, for example, pass over. You don't need to chip it or anything. It goes well like that, and so on. And then indeed, for example, when reading data from these new, for example, we have this Inspire directive for European Union that basically has standardized how data can be, well, the governments are basically distributing their open data sets, spatial data sets, using specific standard. So they are always kind of how you can get that data. So the file format is actually a JSON. So you can actually GeoPandas reads those, reads those automatically from URLs, for example. So you can basically just pass a certain URL address to some specific data from some, for example, Statistics Finland, and you can read it in to GeoDataFrame directly from the web, which is quite powerful thing. So GeoJason is good format, but of course there are these GeoPackage, for example, which is a bit more complicated. So it's kind of a database, so you can have actually different layers there, and then you can also have like raster files and vector files mixed and so on. So that can be also used, but it's a bit more complicated thing to do. But yeah, that's maybe a couple of reasons why, or how do they differ. But still, both of these layers exist more or less, and they are widely used. So good. Any other questions? If not, so let's see how we can actually aggregate data. So basically, this means that we are merging the geometries into one, like, well, if we have polygons, so we are creating a multi-polygon basically out of, based on some common identifier. So what we are doing next is that we are basically aggregating the travel time data in a way that, if we think about that, we have a lot of those grid cells that are polygons in our data, and of course, for example, 10, like the travel time 10 minutes, so we have multiple of them. So we will basically combine those together and then see what we can actually do with them. So let's see how we can use this function called dissolve to do the aggregation. So we can continue working with this intersection data file. So we have intersection.head. So indeed here, as we can already from here see that, for example, this car MT and car RT, so these two have same value in this column, so 46 minutes. So we want to basically put these two rows together and reduce the amount of data in a way that all of these are basically under the same polygon. We can see that they are still different because, for example, the distances differ. So although the travel time is same, the actual route that has been taken is different in these two. Good, but let's do the aggregation. So aggregate data based on common identifier. So we can use exactly this dissolve function. So let's create a variable called dissolved equals to, and the intersection is indeed the data that we want to use, continue using. So we can say that intersection dot dissolve, and by what? So there is a parameter called pi, and here we basically say that based on the values of which column do we actually want to do the aggregation. So let's use this car RT, so car rush hour times, and this is the one that we want to do. And let's print out the dissolved, or we don't need to print, we can just take dissolved dot head, so we can see what happens. So now it took a second or so, and now what we have in here is that we basically seem to have similar kind of data, but now let's see if we compare the number of rows in the data sets. So let's print the length of the intersection layer, and let's print the length of the dissolved. So now what we can see is that in the original data we had 3,826 rows, but now in this new one we actually have 51. So we have actually taken a lot of data and put them together to actually reduce the number and merge those values into together. So we have kind of simplified the data quite a bit, or not simplified, but kind of aggregated. Yeah.
So it's working like group by.
It's kind of working like group by in a way.
What does it do to the other columns? Like how does it treat the other columns to make it?
That's actually a good question. Well, let's continue with next thing. So yeah, we will actually come back to that. So we will see. Well, first of all, what we can see here is that let's print, or not print, let's take the dissolved. So this is now the end result. So dissolved.columns. So what we can see here that, well, yeah, we have these column names that we have, but the one that we used for doing the dissolve, so doing the aggregation car RT. So actually that is now missing from the columns. So we have car MT, car RD, but not car RT. And what is the reason for that? Is actually that if we take a look, what is the index of our dissolved GeoDataFrame? So the index is now actually the values from this car RT. So the values didn't disappear anywhere, but they are now actually used as indices in our data. And this is actually quite useful because now we can basically pick any number which is basically now travel time. So for example, we can take all the geometries and all the rows that belong to the 15 minutes kind of travel time grids. So let's see, for example, that select the grid cells with 15 minutes distance from distances, travel time from railway station. So now what we can do is that we can create a variable called select 15 minutes equals to dissolved 15. And let's see what we have in here. Select 15 minutes dot head. Dissolved dot ilog. So now, so what we are using, so there is the log functionality that we have seen quite many times that wants to have a range of rows, so we could do it like this, but with this .ilog we can just specify certain index position such as 15, and what it will do is that it will actually return that one. But now the question was that what does it actually do with all these values? So in our case, this is a geometric operation that what we are doing here. So we are basically getting what it does is that it creates a multi-polygon from all those polygons and merges those together. But then what actually are these values in here is a good question. It might be that it just takes the answer is that I don't actually know what it does for those columns at the moment. So it might be that it just picks the first one in there. Let's see if we actually have the documentation. geopandas.org is a place to look for, let's say, aggregation with dissolve. What dissolve does is that it does three things. It dissolves all the geometries within given group together into a single geometric features using unary union method. It aggregates all the rows of data in a group using groupby.aggregate, and it combines those two results. So let's see, pandas group by aggregate. So this is what it does. No, I think it's most likely this. Here doesn't have any. Does it have any? No. Yeah, this doesn't have any default function, but or parameter. How would it use that? Mentioned here. Well, I will check that because it's a good question. Anyway, this is kind of the function that it uses, but it doesn't indeed say here how does it actually do with all those values in here. It might be that it's just the first. There typically, if you have used ArcGIS and this dissolve, so the default kind of how it is done is usually kind of the first appearance, and it just takes that. You could take sum, mean, whatever of these things, but I don't know now what does this to. I would assume that it's the first appearance. Good question was that. Good. So, but yeah, so now what we have done is that we have selected indeed those 15-minute grid cells. So let's see if we actually plot those ones. So as we can see, what is the type of this? We can take a look. So type select 15 minutes. We can see that it's pandas series. So this basically, now we can see that we are not anymore working with GeoPandas. So these are not GeoSeries, but this is kind of a row from pandas. So to be able to actually plot these things, we need to first, we have the necessary information in here. So we have the geometry, so we can actually plot these things on a map, but we need to convert this pandas series to GeoPandas and basically create a GeoDataFrame from this. So let's create a GeoDataFrame from the selection. So let's create a variable called geo equals to gbd.geoDataFrame. These are kind of, you have already, well, at least once seen how to create a GeoDataFrame from scratch. So this is now kind of repeating that. So when you create a GeoDataFrame from scratch, so you just create it using gbd.geoDataFrame, and then what it wants to have as an input is basically the values that we want to insert inside this GeoDataFrame. So what do we want to put there is that this is now only one row. So basically it's only one dimensional thing. So we have basically the column names and then each column has some value. So we have key and value. So what we want to put as an inside is that we would put a list of the values that is inside this selection 15 minutes. So with this cell 15-minute dot values, so let's see actually what that does so that you can understand. So what this does is that it basically just makes a list of, or not a list, but an array of all those values that are located in this select 15 in here. So we pass these values inside a list into this GeoDataFrame object. We specify that the coordinate reference system is the same as from this dissolved.crs. Then we specify that the columns in this GeoDataFrame will be the same columns as in this dissolved.columns. And let's take the head of this one. So now what we can see is that we converted this Panda series into something that is now a GeoDataFrame. So we are kind of back in the in such format that we can use, for example, for doing plotting. So now we can plot the grid cells that are 15 minutes away from the railway station. So we can say that well, let's say x equals to, let's first take the dissolved.plot, so let's plot that under, and let's say that the face color equals to gray, and let's plot now these ones on top of it. So geo.plot x equals x, and let's say that the face color equals to red. And now what we have here is that we have basically selected all those grid cells where the travel time is 15 minutes, and we could do this for any other other value that we had on that that GeoDataFrame. So where we, just to kind of repeat one more time, what we did was that we used the dissolve to basically organize the data in a way that the index values are all of those geometries that belongs to one travel time group, basically. So, and then we took one of those groups, namely the 15 minutes, So take all the values where the travel times is 15 minutes, and then we basically plotted those like this. So that's kind of how we can use dissolve to do things. For example, how this could be useful is that, for example, if you think about you have some data, for example, that are let's say that you have in Africa, in every country, you have some administrative borders, and then you want to instead of actually using those small regions within each of those countries, you want to, for example, do the statistics or the analysis based on countries. Of course, you could always download data like the countries, but you could always kind of dissolve the data in a way that kind of upscale from that administrative border level to country-based levels, and then you could do the same. For example, see what is the average age or whatever you want to do with the data. So these kind of geometric manipulations are easy with these aggregations and the dissolve methods that we have. Good. Any questions about dissolve? We have very quick last thing to do if there are no questions about this one. So as the last kind of trick, what might be sometimes useful is to see how to simplify geometries. So indeed, the idea that we have is that we want to take as an input a river from South America, mainly Amazon River. I did my master's thesis sailing somewhere here for quite many days. I did some GPS tracking, so that's the reason for this example, so it's familiar for me. But indeed, now let's see how we can actually convert this river quite detailed kind of curvature into something more simpler geometry, just to demonstrate that this is possible to do. So let's first import, well, we have already the GeoPandas in the memories, but just to make things settled, so I import GeoPandas in here, and let's read the data. So file path. So we have this data, and we have this Amazon River .shape file in there, and then we can read that with the GeoPandas. So with the read file FP, we can check some values from there, such as print the coordinate reference system, what CRS, and then we can plot it. So we can say that data.plot like this, and now we see that okay, this is how the data looks like. So we have the river in here. We can see that the coordinate reference system well, we can see the projection is Merc, so it's Mercator. The important thing here is that the units are in meters in this case. So as we can see from these values, so they are meters from somewhere, these ones. And from somewhere we have the longitude -43 and the latitude is -2. So this is basically kind of the central longitude where those distances have been calculated from. So that's the idea. So it's a Mercator projection based on this Circus datum. So if we click on this, it's this kind of Brazil Mercator. used. Yeah, but anyway, so what we want to do is that we want to generalize these geometries a bit, and what we can use for doing that is a function called simplify. And let's generalize the geometry, and we say that data, so we are creating a new column for this geometry that has been generalized. So let's create data geom_gen, such as generalize, and we can say that data dot simplify. And there is a parameter called tolerance that can be used to specify basically a threshold that how did it now go? But anyway, this is kind of the threshold, like how much the geometry should be simplified. Let's see if we actually have the yeah, so all points in a simplified geometry will be no more than tolerance distance from the original. So basically it will take a look at this distance, and if things are less than this distance, it will kind of simplify those nodes in the line strings or polygons or whatever you have. So let's specify that the tolerance is 20 kilometers because, well, Amazon River is fairly long, so we can actually specify quite high tolerance distance in here. So we can do that, and then we can plot what comes out. So first of all, let's set the geometry after this to be this new column. So we can say that data equals to data dot set geometry, and the geometry will be taken from this geom_gen, and then we plot data dot plot. And now what comes out is that, well, as you can see, if we compare this one to this one, it simplifies it quite a bit. We can also see and test if we simplify it even more, or let's say like 50 kilometers. So we can see that it actually takes and reduces the dimensions quite a bit. If we say like if it would be like 5,000 meters, so 5 kilometers, why doesn't it maybe read this again? Yeah, so if we put 5,000 meters, so it actually doesn't do much in here, so it's not that visible to see any changes in here, but probably there has been some reduction in the, or some generalization in the data. Good, but those are kind of the things that were the topics of this week. So a few kind of useful data rank or data processing approaches. First of all, doing the tabular data processing, and then doing some geometric operations on the data. Then we have exercise 4. It's not yet online, so I will put it tomorrow online, so you can take a look. It will basically follow the one from last year. So we can take a look. AutoGIS 2017 exercise 4. So it more or less follows this one. So what we will do is that we will kind of use the travel time data and do some visualization using those classifications. So indeed kind of repeating the things that we went through. so using Pysal, or create your own custom classifier. Then the idea is to calculate and visualize dominance areas of shopping centers. So basically what you will have is that you have travel time information for multiple locations in Helsinki region. So this is something quite often or typical things to do in economic geography, that you want to understand the kind of dominance area of different, well, in this case shopping centers, to understand that, okay, which areas are dominated by this shopping center. And we can basically, well, there can be sophisticated models to do that, such as gravity-based models, but what we are now just doing as a simple example is to specify the dominance area to be where the travel time is the shortest. So that is kind of a process that we will do in here. And then the idea is to again continue from this kind of practical example, is to understand that, okay, if we have this dominance area for certain shopping center, well, how many people are living there? So these three problems will be the one that you will do. Yeah, but that's about it. Any questions about exercise or anything? If not, so on Thursday there will be the practical session again. We haven't yet, I think, produced any feedback from the exercise 1 or 2, but we will do that now during this week. Hopefully at least start to produce those feedbacks from them. And until Wednesday you have still time to work with the problem or the exercise 3. Good. Okay, but that's it. So